Assalamu alaikum all. In the previous video, we discussed about the construction of solar photovoltaic cells. In today's videos, we will study the working principle that how a solar photovoltaic cell converts the sunlight energy into electrical energy. Okay, when the light, when the sunlight in the form of photon falls on the N-type layer, as we discussed, that N-type is the top layer. So the N-type layer is very thin, so it penetrates to the depletion region. In the depletion region, the photon or the energy is absorbed by the electron in the silicon atom. So when the electron absorb energy, so it will excite and it will leave the valence shell and go to the conduction band. Yes, we will explain there that as we said that these are, for example, this is the N-type layer, this is depletion region, and this is P-type layer. This is P-type layer, this is N-type. Okay, so this is depletion region. This N-type layer, we will extend this. This N-type layer, as we said, that this is doped with pentavalent impurity, so it has more number of electrons. And P-type, this has trivalent impurity, so it has holes. Holes mean deficiency of electron, or we call it behaves positively charged or hole. Okay, so we consider it for simplicity as a positive charge. So when these two material are combined at the junction, at the combining point, as we know that N-type material have excess of electron and P-type have deficiency of electron. So from this N-type material, from this N-type layer, electron will move toward the P-type layer. If we so this electron will move from N-type to P-type. So electron will accumulate it here at the surface, at the junction point. Electron will accumulate it here, so it will be negatively charged, and proton will be a positive charge because positively ion, so this will be positively charged. This side will be positively charged because there is the deficiency of electron. Electron leave the valence shell and move toward until equilibrium occur. These electron move toward this N-type material, and as long as when the equilibrium, so further there is no due to the electrostatic field, no further electron will move toward the P-type layer, and there is a field developed between this N-type and P-type. And the direction of the field will be from the N-type to P-type. Okay, there are silicon atoms. Okay, so for example, there is this is valence shell. Valence shell has 4 electrons. So when the sunlight, we will use another color to easily understand. When the sunlight in the form of photon is nothing but energy packets. It will penetrate to the depletion region, and this energy will excite this electron to become free from the valence shell or valence band. So this electron will be free. So there are a lot of electron and holes are created. Holes and electron are created. Holes, as we say that hole we consider negatively, uh, positively charged particle, and electron, we consider electron are already negatively charged. So due to opposite charges, electron will move toward the positive charges because the field is electron. Negative charges will always move toward opposite side of the direction, opposite side of the field. Okay, so this electron will move toward the electron will move due to the field present in this depletion region. Electron will move toward the n-type material, and proton positive hole will move toward the p-type material. So if we connect, there are bus bars. If we connect a resistor external load to this p-type, so electron will move from this side, from this inside toward, and go past through the external load to P side, and this current will continue as long as the photon or the light falls on the solar photovoltaic cell. Okay, so as we discuss the direction of the field, we discuss how photon eject electron. Now one term is the band gap. When if photon energy is greater than the semiconductor energy, so it excites electron, the valence band to conduction band, creating electron hole pair. For example, this is the last shell, this is nucleus, and this is positively charged. And these are, for example, more shell. We will not draw. And this, the last shell we are interested in, the last shell, we called it valence shell. For example, there are 4 electron in silicon because according to the periodic table, the outer shell, for example, if any element is in the any group, one group, so it have 1 electron in the outer shell, all the atom. In the third group, so 3 electron in the valence shell. Okay. These electron, for example, sunlight, and this atom, let's suppose this is in the depletion region. We call this depletion region. Sunlight come, okay, strike the n-type layer. After that, it pass to the depletion region, and for example, this packet, this photon reach this electron, and this electron absorb the energy. So this electron leave the atom and go to conduction band. Go to conduction band. It will now flow freely, and it can be a part of the current. Okay, and this will be left behind. So this whole atom, we call it whole, or we consider it as positively charged because there is deficiency of electron. So when for example, this electron is held by the nucleus in the stable shell by the nuclear electrostatic force, nuclear force. Okay, so when the photon reach, so if the energy is more than the band gap is measured in electron volt. Electron volt is a small unit of energy used for elementary particle. Uh, for example, joule is a larger unit, so we not use the joule for elementary particle like proton energy, electron energy. So this, when the proton energy is greater than the band gap, so it will excite the electron and move toward the conduction band. Okay, and due to the we already discussed that there is field already present. So due to the field, the moment the electron move toward the n-type and proton move toward the p-type. This valence band and conduction band creating an electron hole pair. We studied that the band gap. Band gap is the amount of energy in electron volt when it's required to free the electron from valence band or from valence shell to become free, or conduction band. This is band gap. And the voltage, the separation, the built-in field between silicon is 0.5 to 0.6 volt. This is different with different material. For example, if it's germanium silicon, so the built-in field will be different for different material. The optimal band gap is 1.4 per this silicon. Optimal band gap for silicon is 1.4 electron volt. Uh, when the photon energy is greater than the band gap, so extra energy will be dissipated as heat. When it is less, so it will not eject electron and not will eject create electron hole pair. So we cover all these points. These points we cover. All these we cover. The extra is this. This the sunlight covers a broad spectrum 0.5 electron volt to 3.5 electron volt. These are the energies of different photons. Now, types of photovoltaic cells. There are three types of photovoltaic cells which dominate the world market. Broadly, this is divided into two types. One is one is crystalline, and the other one is amorphous solar PV cell. So, crystalline is further divided into two: monocrystalline and polycrystalline. Monocrystalline are the most advanced and the higher efficiency, but it is very costly. So its efficiency is 22 to 23% now available in the market, commercial market. In laboratory, we can achieve higher efficiency, but it is not available commercially. So, for example, if 100 watt of light energy in the form of light energy fall on a solar cell, so it will convert only 22 to 23%, 22 to 23% to DC electrical energy. And polycrystalline silicon, which is like polycrystalline, has efficiency, for example, 19 to 20%. And thin film, we discussed this one. This one is amorphous silicon cells. Its efficiency is 10. It is the cheaper than the monocrystalline and polycrystalline. Its efficiency is, for example, 10 to 12%. Higher efficiency few technologies, including gallium arsenide and multi-junction cells, are less common due to their high cost, but ideal for use in concentrated photovoltaic system in space station. For example, space station and any other facility or any other requirement, which is the main focus is efficiency, and there is efficiency is required to achieve higher efficiency, and there is no such a big area. So then it is worth it to use highly and costly solar cells. Okay, in space station we have larger power requirement and small area, so that's why we use multi-junction or other technologies to achieve higher efficiency, more than 22%. 23% are very less as compared for these applications. Types of photovoltaic systems. We will discuss each, but here we will shortly describe these three types, and then we will discuss each type in detail one by one. On-grid system or grid tie or grid feed system. It is also these are three names interchangeably used. On-grid, grid tie, and grid feed system is a solar system which is connected with utility grid and not need a battery bank. So for this system, we not no need of battery bank. Then off-grid, which is also called standalone system, is a solar system which is not connected with utility grid, and the system has energy storage for the night time. If like remote areas where there is no power supply, we can use this system, which has for the night time, which has energy storage. And hybrid system is a system which is connected with the grid, utility grid, and has also the backup source. When grid is not available, it works like off-grid system. So I shortly we will explain these in detail. Uh, so I shortly explain these now. For now, uh, inshallah, see you in the next video. Thanks for watching the video. Like the video, share with your friends, and subscribe our channel. If you have any doubt or confusion, please ask in the comment section. Okay.